So this is a Plyo Floor, or plyometrics floor, and is commonly used by triggers everywhere. It works by converting an athlete's kinetic energy to elastic potential energy, causing it to deform and absorb the shock before sending it back as kinetic energy. The time it takes the floor to deform and transfer back the energy lessens the impact on joints, as well as adding speed to tricks. Although the gravitational force is the same, on a regular hardwood floor, the force exerted upon landing is absorbed by the athlete's joints almost immediately, rather than first being absorbed by the floor before being given back to the athlete for takeoff. With a plyo floor, there is better conservation of energy because it is given back after a slight delay, which causes the energy to be put to good use during a skill, rather than being taken in by the joints. The surface of a plyo floor is also textured with small ridges, like a carpet. This increases the static friction versus a hardwood floor and makes it much easier to land and take off from tricks without slipping. Observing this flash gainer, the maximum speed of the driving leg occurs as it kicks upwards, before the other leg has left the ground. The instant at which it changes direction from swinging down to swinging up, the speed is 0 meters per second. After that instant, the maximum speed must be reached in order to get the system, or in this case the athlete, off the ground and complete the arc. Following the maximum speed of the driving leg, the succeeding speed remains constant in a conservation of momentum until it reaches the ground again for landing. It is clear that the maximum speed occurs at this point because the leg drives upwards very quickly and maintains the same speed once the back leg is off the floor. In order for the athlete to gain the height needed from the setup, the first leg must swing through very quickly so that the rest of the body is able to get off the ground, at which point the speed is constant as the leg makes an arc-like shape through the air to reach ground level again. We can see in this cartwheel back handspring that the acceleration occurs right when the athlete takes off with the second trick. Here, we can see that the speed of the legs is 0 meters per second, while the knees are being bent in preparation for takeoff. Now, we can see that the athlete is jumping backwards onto the ground. The acceleration increases to launch the legs over the body and propel the entire system in an arc-like shape. It is clear that the acceleration occurs at this point because the speed of the athlete's legs increases from when they are on the ground bending at 0 meters per second to when they launch for takeoff and kick over the body. Acceleration must take place because without the forward arc-like momentum that the legs carry after they jump, the center of gravity would not be maintained and the athlete would not be able to land the back handspring properly. For this raise, we can follow the path of the left leg as it takes off from the ground, forms an arc through the air, and returns to the ground for landing. Although there is a greater distance traveled in the air, the resultant displacement can be measured in a straight line across the floor, this being from where the left foot took off to where it landed. The path is visible if the ground is observed throughout the skill, as opposed to watching where the left leg goes in the air. It can also be calculated by taking the total height and angles reached by the athlete. The distance traveled horizontally along the floor is necessary for maintaining the momentum and speed of the raise. Without this lateral movement, the conservation of momentum in the trick would be less efficient and therefore would not be as easy to add into combos as shown here. To solve for the vertical acceleration of the left foot up to this halfway point before it changes direction, we must rearrange this equation and substitute in the variables. The initial speed is 0 meters per second because the foot started from a jump takeoff as opposed to a swing. The vertical acceleration of the left foot is 4 meters per second squared up. For this J-step gainer, let's find the maximum vertical velocity of the driving foot. The initial velocity is 0 meters per second since there is no vertical velocity when the foot is at the peak height of the trick as shown here. After calculation, it is clear that the max vertical speed of the right foot is 7.6 meters per second downwards. If we look at this gainer again, using a different formula we can calculate the vertical acceleration of the right foot. Using the distance in the previous formula and time taken from when the foot was perpendicular to the floor to where it is now, parallel to the floor, the acceleration is calculated to be 25 meters per second squared downward for the driving foot. To find the acceleration of the first foot, the time and distance from when it takes off to when it touches the ground again must first be obtained to calculate the final velocity. After rearranging this equation, substituting in variables, and solving, the horizontal acceleration of the left foot is determined to be 0.9 meters per second squared to the right. Newton's first law states that an object in motion stays in motion, unless stopped or slowed by an opposing force. Trickers use this law to their advantage to control their body's position and speed in the air, as well as transitioning from one trick to the next. If a tricker were to open up their arms or legs, as often seen at the end of a skill, the inertia would increase and the athlete would slow because the mass is farther from the axis of rotation. The angular momentum is conserved when the athlete's limbs are wrapped tighter and their inertia would decrease, allowing them to spin faster. If the tricker wants to increase their height during a skill, they must apply more force. Newton's second law states that force is equal to mass times acceleration, and since the athlete's mass cannot change, they must increase the acceleration going into a trick in order to up their force. In this trick, the athlete can control the swinging leg shown here and its acceleration in order to gain height and reach the ground faster. When a greater force is applied, it is easier to transfer through each trick in a combo. If a tricker with a greater mass were to do the same skill as one with a smaller mass, both applying the same acceleration, the one with the greater mass will apply more force into the trick. As the mass or acceleration increases, the force will increase as well. When a tricker rebounds off the Plyo floor, the reason it doesn't shatter on impact is Newton's third law, stating that the force exerted onto the floor is returned by an equal or opposite force. Here, when the athlete jumps, she compresses the floor. As the floor decompresses, it exerts an equal or nearly equal force back to her, which gives the momentum needed to complete the skill. The action force and reaction force are both equal in intensity, yet in opposite directions. This exchange occurs whenever the tricker takes off or lands a skill and is vital to the sport. If the ground were to absorb all the force exerted onto it, the athlete would not gain any height or speed and would fail to perform any tricks at all. Friction is a significant element in tricking. The floor many athletes prefer to use while training is lined with small carpet-like ridges, giving it a rough texture. Static friction takes place before the tricker has taken off for the skill, preventing them from moving. It is stronger than kinetic friction and is dependent on the mass of the athlete and the material of the floor. The greater his or her mass, the more force is required to overcome the initial force of static friction and begin moving. Training on slippery surfaces, such as concrete or wood, increases the risk of falling and therefore injury, since they have less kinetic friction than a plyometric floor. This makes it easier to slide and move across, but more challenging to land tricks properly because the static friction also decreases. It is often visible whether the athlete is on a floor with an increased frictional force or not. Usually on smoother surfaces like hardwood, trickers train in shoes with rubber soles to provide more grip and cushion the impact. This is not necessary on a plyometric floor. Also, their tricks may land with less stability and power, given the nature of these more rigid surfaces. As the swinging leg in this gainer rises, the potential energy increases. At the peak height, its potential energy is 100% of the total energy in this presumably closed system, while the kinetic energy is 0% on the vertical. Once that leg lands, the roles reverse, with the gravitational potential energy being 0% and the kinetic energy being at 100% also vertically. This occurs because at the foot's summit, the amount of work done to raise the leg from the ground to the top is representative of all the energy contained in the system. As the leg lowers and the height decreases, the potential energy is transformed into kinetic energy until the ground is reached and no potential energy remains. Energy conservation states that the total amount of energy at both points will be equal, just in varying forms. We can see that on a hardwood floor, much of the energy put in is converted into sound energy instead of kinetic. This occurs during takeoff and landing. It is audible and can be noticed by the lack of height, compared to a floor with a more efficient material such as plyo, which keeps more of the energy functioning within the system, giving the athlete more energy to use in the skill itself rather than lost to other means. The power of this gainer is the work over the time taken to complete the skill. It occurs throughout the entire trick. A weaker athlete, or one putting in less work, would complete the trick over the same amount of time but have less power. Or they might achieve the same amount of work shown here but do it in more time. Time and power are inversely proportional. The difference in power between the two tricks would be visible because the one using less power would be doing work at a lower rate. A certain amount of power is needed to properly perform the trick because without a sufficient amount, say, too much time taken, the momentum would not be maintained and the driving leg would not be able to land on the ground while the athlete is upright. The skills done in front of this wall were analyzed with the help of 3 measurements: a vertical height, a horizontal distance, and time. To measure the time spent in the air and taken to do the trick, I used Sony Vegas Pro because of its accurate timekeeping properties, which extend to 2 decimal places. I measured out every foot for as far as I could reach, both horizontally and vertically, to see how tall and far each trick traveled. These were measured with chalk. Here, I was able to slow down and crop essential portions of the skill for my needs, which allowed me to determine the height, distance, and exact time. This data was used in the kinematics, forces, and energy portions of the video. To measure the height and distance reached in this clip, the height of the athlete was found with her arm raised to full extension. Then the angle reached during the cartwheel was accounted for using the trigonometry shown here. This is the max height during the skill. Finally, Adobe Photoshop was used to visually represent the calculations and diagrams. Then, Sony Vegas Pro was utilized to edit the clips found in spare footage and samplers.